Thanks. I want to thank everyone for coming here today. I know it's early in the morning. It's tough to wake up and make it to this talk, so thanks for everyone for getting here on time. So my name is Gutierrez. I work for Gotham Digital Science. We're an application security company. We pretty much do all things security. This talk is going to be talking about secure containers, and primarily in the iOS world. So we're going to talk a lot about iOS concepts for building these iOS secure containers. It's not going to be a iOS 101 kind of presentation. So it kind of assumes that you have a base knowledge of iOS and then tries to build on top of that. So just a quick outline of the talk. First, we're going to talk about, what are they? Secure containers is a pretty broad topic. Let's define what a secure container is and then work off of that. Then we're going to get into how commercial solutions out there and also homegrown solutions are actually developing these secure containers. Talk about some authentication design patterns and data encryption best practices, assessing the strength of a secure container. You see a secure container out there, a solution, or you want to build your own. How do you determine how good it is? And what are some limitations available in iOS that can limit how effective a secure container can actually be? So I'm sure most of you have heard of the BYOD, bring your own device. A lot of enterprises are now embracing this new concept, and if you're not familiar with it, the concept is that you can now use instead of like an organization providing you with a device, you can now use your own personal device to access company resources. And unlike a managed device, the company no longer has the ability to enforce policies on you. So where did BYOD come from? Essentially, back in the old days, BlackBerry was like the de facto device that organizations had. It had the best way for the organizations to actually manage policies on the BlackBerry device. It had excellent software to do that. But as times progressed, more and more other cell phone people started having smartphones on them all the time. So an organization started thinking, why are we having our employees carry around 2 devices all the time? They have a perfectly capable device already. Why not just have them use that one instead of spending company resources buying these BlackBerries, buying the BES server to actually manage these? So as a cost-saving measure, they've actually starting to embrace this BYOD approach. So what is a secure container? Let's actually define this. Let's assume that it's going to be something that provides the data security at the application layer. Since I can't control the device policies, I'm going to control security at an application layer, and everything within that application I'm going to want full control of. It can't rely on any OS security policies or features. So even if a device does not have a passphrase, for example, my app's secure container should still be secure. And it should still allow me to enforce other types of policies as I wish. So what are some of the big name BYOD solutions out there? You might have heard some of these, like Good, Citrix, there's Nucona, which is part of Symantec, and Mocana. We're going to talk about some of these solutions and go into how they actually work and some security issues that we've encountered in some of these. So once again, the main reason why companies are starting to look into research for secure containers and these commercial solutions, they want their employees to have access to their data all the time. One of the best places I do my personal reading is when I'm in the bathroom. I have my cell phone with me all the time. I'm there. So companies are like, why are we not, we want them to be doing company work on their personal devices. Why not enable that? So what are the main issues with unmanaged devices? The main risks here are, I can't control that user from setting a passphrase. And setting a passphrase in the iOS world means that it enables data protection. And for those not familiar with data protection, this is the main API that iOS developers can leverage to actually protect data at rest. It encrypts the data using a passphrase that's derived from the passcode on your device. So if you don't have a strong passcode or any passcode, you're not, like, developers really have no built-in solution to actually protect data being stored unless they roll their own encryption, which, you don't want to have all your developers and applications have to do that. It's kind of hard. Other policies, of course, are, like remote wipes. I don't manage that device. What if it gets lost or stolen? How can I trigger a remote wipe? And running on a jailbroken device, when you're running on a jailbroken device, all the built-in iOS security features no longer exist. So it's a big security risk. So let's get a little more technical and figure out how these containers actually work. They leverage a concept called application wrapping. And what this actually does is, you have an existing app, a developer has created it already. I want to wrap it and make it more secure. So it's going to actually inject new functionality into an existing application. And this new functionality is going to be used to add data encryption at rest, add authentication, and enforce any other policies that I really want to do. And one of the key things is I never have to have access to the code if I don't want it to have access to the code. But if I have access to the code, I can still pull this off as well. I don't require any changes to the code. So this is a very high-level diagram of essentially how app wrapping works. Organization, they say, all right, there's a lot of good apps out there on the App Store. You have a mailbox application. I want them to use that to read their mail. I want them to use the iAnnotate application to read and edit PDF files. There's a Docs2Go application to read and edit Word documents without having to worry about, are these applications secure? How are they storing data? I can't enforce authentication on these things. I don't want them reading my sensitive company resources from these applications. I'm going to actually wrap them and ensure and enforce the policies that I want. And then it spits out a brand new version of that existing app that's actually secured and locked down. So let's look into how Citrix Cloud Gateway does it, which is their secure app store, basically. The way, from a very high level, the way it works is you have an IPA file of an existing application. You install this app wrapping tool software on your MacBook or whatever. It then accepts that IPA file, accepts a new iOS distribution certificate, and then it spits out a brand new IPA file. Very pixie dust magic. But now let's actually analyze the before and the after and find out what exactly it's changing and how to do this. So the first step we did was we took the two actual binary executables and then we did a hex diff on them. And I used Hexfiend, which is some free tool out there. And using this kind of highlighted what in the binary was actually modified and determined what address offset in that binary was the actual change. Obviously, the hex is not very user-friendly. It's not very readable. So the executables that actually run on iOS and macOS 10 is the Mako executable. You might be familiar with like ELF executables or PE executables. This is just the iOS version, the one that iOS runs. So you can just pop this. Mako executables have a defined formatting. So I pop it into a tool called Mako View that just kind of outlays the actual formatting of this executable in a nice human-readable format. And then I hone in on what was actually added in the resulting executable. And what was actually injected into it was a LC load dynamic library. So what is this doing? It's actually it injected into the existing application saying, I want you to now load this dynamic library as well. So when it runs, I'm actually injecting code at that point in time. And then when we look to see where this dynamic library is, it was pointing to a new one that it actually injected called the Citrix dylib, which it should just packaged alongside with the binary in the same IPA file. The next thing that changed in the executable was the code signature, which is what we expected. Because in iOS, everything has to be signed in order to run properly. So as I mentioned earlier, I had to specify a distribution certificate as well. So I had to re-sign the application so that I could actually run on a device. And that makes sense. So another thing to keep in mind is that when you're submitting to the App Store, you can't actually use dynamic libraries. It's banned. So you can only ever release these wrapped applications within internal like enterprise application stores. So as long as you sign in with your own distribution certificate, you can pull that off. So let's get into, I now have code execution in this binary. I injected my dynamic library. How are they overwriting functionality built into that app? This docs2go application is, you're editing Word docs and it's saving them to the file system on the device. How is this dynamic library actually changing that implementation of the file system right to add this encryption? So this technique's called method swizzling. And if you're familiar with like iOS hacking or jailbreak development, you might have heard of like mobile substrate tweaks or SciScript that kind of do the same thing. And behind the scenes, they're all just leveraging method swizzling techniques for Objective-C. So let's look at the application lifecycle for iOS. You install an app, you want to run it. You click the start icon. It then calls a UI application main. Application main then provides you with an application delegate, which is a protocol. Every single iOS app has to define their own application delegate. And this is just going to contain a bunch of methods that get triggered upon this event loop. So the event that gets triggered when you start an app is the application did finish launching with options. Since this is one of the first things that gets executed when you start an app, this is like the most interesting place to actually start our injection. We want to try to swizzle this method and change the implementation to whatever we want. So how do we do that? How am I injecting into something that's executed that early in the life cycle? Objective-C method objects have this useful method called load. And what load does is the moment that that library actually gets executed, it'll actually run this code on every single object within it, as long as it's implemented. So since I can control and inject the library, as long as I implement load, I can then inject even earlier in the application lifecycle and do whatever I need to do. If I want to replace application did finish launching, I can then replace it with whatever I want. So swizzling is as easy as these three function calls. You start off with a original. You want to get the original method. So if you call a class underscore get instance method, first parameter is just the object that you want to replace and the method as well. And then you specify the method that you've created that you want to replace it with. And then lastly, you have method exchange implementations. And all it really does is just swaps the implementations. So now when the app, the executable is executing the original one, it's executing my code instead. And then when my code decides, I want to run the original, I'm just going to run myself, and it's just going to run the original behind the scenes. Yeah, it's like this allows me to just inject right before the original method. I can do whatever code I want here and then just call the original so the app doesn't break. All right, so first demo is just going to show you a POC for method swizzling. Let's say your organization has a bunch of applications. I'm going to show you an example of how to create a static library. You have the code. What if I said you can take the static library, link it with your existing applications, and then suddenly make it more secure? So this will be like a little POC of how to actually pull that off. So here we have existing banking application. It has its own definition of application did finish launching. Great. But this is where I want to actually start injecting. So we run the application. It's your typical banking application, right? It does the typical functions that a typical banking app would pull off. So now our goal is I want to replace the functionality of the application did finish launching, which is showing this UI, and inject a login screen right before it actually runs. So now I switch to the code of the library that I'm creating. One of the main starts off just writing something to the console. So the first issue is, how does my static library code, which doesn't have any idea the name of the class that you named your application delegate? How am I supposed to swizzle it without knowing the name first? So the first thing we had to do was retrieve a list of all the classes available in the executing program. So that's what that obj copy class list does. I then iterates through all the classes. And as I mentioned earlier, every single app delegate has to follow a protocol of a UI application delegate. So I just do a simple if statement that says, does this class conform to the UI application delegate? If yes, I've probably found the right class and I want to start swizzling. Once I found that class, I then do exactly how I showed you before. I do the method exchange implementations. I now swap the implementation. At this point, my swizzled method, which is right there, it's just going to add, instead of the original view controller, it's going to throw in my login controller. I can do whatever logic I want to do at this point in time. So I can swizzle, now what? This is just a POC showing how to easily start implementing your own. Obviously it's not doing any security, fancy schmancy stuff, but now you have code execution into an app. What can you do? Add in your own SSO authentication to your app. You have all these apps in your organization. Why not just have a library that they can use to actually, you can just plug and play and then take care of the authentication for you? Or what if you want to add data storage encryption? All you have to do is swizzle the implementations to like all the file system rights, the SQLite database rights, so on and so forth, and then add security that way. And apparently there's a market for these type of things based on all these BYOD solutions out there. People are doing this and actually selling it out to make large profits. So we'll get into authentication design patterns. So if you're going to add data encryption to an application, how is that key being generated to actually protect the data? And I think that's the main thing you have to worry about when you're developing secure containers. You're adding data encryption, but like how is that encryption actually implemented? Is it bypassable? And the only way to ever implement proper encryption within an iOS app is you have to have some sort of authentication to retrieve that key value. So some principles to live by when developing secure containers are the data stored in the app must all be encrypted seamlessly. The strength of the crypto can never rely on any device policies whatsoever. And the crypto keys must be retrieved upon successful authentication. You should never be able to retrieve a key without fully authenticating to the app. If you see any of these authentication designs in a solution out there, it is broken by design, no questions asked. Storing a crypto key on a device, it's broken. Crypto key derived out of the entire key derivation material stored on different places on a device. As long as it's all retrievable, it's going to be broken. And data storage not protected by app authentication passcode. So if I don't need to actually authenticate, once again, to get that key, it's going to be broken. The reason why all of these are broken is you're essentially encrypting data and storing the key right next to it. Real life scenario, I bought a nice fancy, lockpick-proof lock, and then I store a key underneath my flower pot. A thief is no longer going to try to break this unpickable lock. He's going to just look for the key that's underneath and just go right through the front door. In the security in this scenario, why am I trying to break AES encryption if the real goal here is to actually just reverse engineer the app, retrieve the key, and then get going? Or bypass logic in the app, say, all right, you showed me a login screen, that's great. I'm just going to bypass that and just use the app anyway. So let's look at an example of an app that has a lock passcode screen, but doesn't actually protect the data derived from the passphrase. So I use the Mint application to host all my credit card info. It gives me nice little push alerts and whatnot. It had this nice little feature to set up passcode, PIN code on it. So I was like, all right, cool. And I thought I needed a demo here, so I tried to spend some time to bypass it. Turned out to be pretty easy. So let's go through it step by step and show you how easy it is to reverse an app. You might think, oh, iOS is hard to reverse. Not really. It's actually pretty simple. So you get the Mint app from the App Store. It's encrypted. Great. There's a lot of tools out there that can decrypt it easily. So I use Clutch. Decrypted binary. I now want to know what are all the methods that are being called in the app. All right, I use a tool called class dump or any variety of it. Prints out a nice listing of every single object and method within that app. Great. What am I looking for now? I want to know what function is called after that pin code lock screen, after I enter the correct pin code. I want to know what method is actually being called to trigger the UI to change to the actual app. So that's my resulting goal. So here's a class dump output. I went to the app delegate. That's usually the first place you look, because that's the starting point, right? I go through some of the method calls, and right away, one of them stood out, and that was the pop away passcode. Great, this looks promising. So I go to my next step. I want to know, when is this pop away passcode being called by the app? I want to know, is this actually being triggered once I enter proper passcode? So the quick way to do this is leverage swizzling, but this time from an attacking standpoint rather than a protecting standpoint. And to do that, we leverage mobile substrate and the Theos framework, which allows you to do quick and dirty hooking of any function you want and just do logging functions or re-implement them any way you wish. This requires jailbroken device, FYI. So this is how easy it is to write a Theos tweak. It takes you about 5 minutes. All you really need to do is specify %hook, what object I want to hook into, and then just re-implement any method within there I want. So I haven't even looked at any assembly right now, and I'm already trying to replace and figure out how this application actually works. So I start off with the pop away with passcode, which is what I'm interested in. I do a %log, which just says log it to the console when this code actually runs. And then do a %orig, which says run the original code once you've logged it to the console. So app will work the way it's expected to work. I just know now by looking at the console when it actually runs. Just look at a quick demo of this in action. There's another tool called SciScript, which I'm going to actually use here to show this. SciScript is an interpreter kind of tool that does this kind of method hooking, and it just gives you a command line interface. And the really interesting thing about SciScript is it allows you to call any code within an app anytime you want. So even though the app's running and it's in the lock screen, I could call any single function call within that app that I see fit. And we'll talk about why that's important in a bit. So I'm running the app. I got it on AirPlay going on my laptop. I decided had the lock screen set up. Well, I'm about to have the lock screen set up. All right, great. So I have an SSH prompt going into my device since it's jailbroken, and I just want to bypass it. First thing you do with SciScript is it requires the process ID of the running Mint app. So I just do a PSDF to get that value, and then I run SciScript to get a nice interpreter that's already injected into the Mint application. All right, I've got my interpreter. As I mentioned earlier, that the Gala app delegates the function we want to start hooking. So I'm just going to create the object from this command line. I can call anything within the class now and just execute it as I wish. So I'm going to call the shared controller, some trial and error, and then I figured out that actually returns a callable Gala app delegate if I create a variable with that. And then I just call the method called popAway passcode. And ideally, if my theory was right, the passcode will just disappear. And then I can just use the application as I wish. So let's take a step back. What if, Mint doesn't do any data storage encryption. So I could have attacked this in a number of ways, but I chose this way because it's important to see the higher level concept of what if it was doing encryption. If it broke one of those principles, those broken by design principles, and the key was stored everywhere, the developers thought they were super slick and they do I'm going to create a key by doing SHA-256 inception on the device ID and some random value here, and then at the end of the day, that doesn't matter. I have full execution ability within the app. if you have a method called generate passphrase or get encryption key, I could have just called that and gotten the encryption key. I don't really need to know how that's implemented behind the scenes if I can just call the method that just returns it to me straight up. Let's look into some authentication designs. It gets a little tricky. How do you implement proper authentication when you want to support both online and offline access? You know, you want online is easy. You're gonna authenticate to a web server. You know that everyone knows how to do that, hopefully, somewhat well. You can retrieve an encryption key from the online server. And why is that good? Because you can enforce server-side policies, lockouts, and all that, and it makes it nice and secure. Now, when we get to offline access, you know, you still want employees to have access to their files while they're in the train station or somewhere offline. So we need to implement a way for them to be able to decrypt that data, retrieve that key, even though they don't have internet access, and that introduces some issues. So the way you can pull this off is kind of similar to how disk encryption works. You have a master key, and then you just have other keys that encrypt that master key and protect it. So the only way you can get access to the master key is by authenticating using one of those values. So we generate a master key upon initial startup. This master key is used to actually do the encryption and decryption of all the data stored on the device. And then the offline passphrase, you pass it through a key derivation function. It generates an offline encryption key, and that encryption key is then used to actually get access to the master encryption key. Same process for the online encryption mode, except instead of deriving it locally, you derive it from the server. What this added benefit of this is you can have separate passwords for online encryption than you would for offline. So if someone somehow brute forces the offline, it doesn't affect your data available online as well. The key for this working, of course, is never persisting the master encryption key or any other key on the device, whether it's file system or memory. And encryption is hard. Crypto is hard. So always beware and have this inspected by a security professional. So what are the main common issues that we've seen in offline encryption modes? Weak key derivation functions. A lot of times we see people just passing it through a hashing function and assume, all right, I got the proper key length. I can use that as my AES key. But in reality, you're making yourself susceptible to brute force. So we recommend the PBKDF2. The minimum of like 4,096 seems okay. But you can tweak this as you wish based on performance. And what this does is it's a function that's somewhat slow, and it's used to generate this encryption key. So it makes offline brute forcing a lot harder. Let's look at another real-world example. This was found in a password and data vault solution we took from the App Store. Not going to say the name because they gave me a nasty lawyer letter. So the way this patched already, but anyways. So the password vault, you store, it's kind of like KeePass if you're familiar with those. You pass in a URL and like the password, your login credentials, and then you have a master encryption, master passphrase that protects all that data. So all right, so we decided to look at it because I was interested in secure containers. I wanted to see how it worked. The password vault authentication was performed using bcrypt. For those familiar with bcrypt, it's a slow hashing algorithm. It's fairly resistant to offline brute force, so great. I was like, awesome. But bcrypt output isn't really something you could plug into as an AES key. So I was like, all right. So then I'm probably not using this bcrypt hash to actually protect the data. So like, how are they doing this? Upon further investigation, this is the Android output from the thing, since assembly is hard to read. It turns out that upon successful authentication, they then took the plain text password, passed it through a SHA-256 function, and then created the secret key value there. So what's the main risk here? You're saying you use bcrypt to protect the passphrase, but me as an attacker, I no longer have to care about this bcrypt. I can brute force the SHA-256 because that's what you're using as your key instead of the bcrypt. So let's look at the time comparisons. So PBKDF2, I forgot to put, I did like 1,000 hashes. So this time is how long it takes to generate 1,000 hashes. PBKDF2 with the 4096 takes 317 seconds to run 1,000 hashes. SHA-256 by itself takes 0.001 seconds. And then in order to exploit this vulnerability, I would need to do a SHA-256 to generate the key, and then do an AES decrypt. Key thing about AES decrypt, they're both designed to be fast. The main purpose of AES is to be fast and secure. So that, as you can see, it still takes very minimal time to actually do an AES decrypt along with the SHA-256. So let's look at the completeness of an implementation. You have a solution out there. They've tried to take into consideration the writing to the file system, SQLite databases, the really common APIs. But what are some things they need to be aware of? There's a lot of subtle OS features that cache data that might not be very straightforward that you should also be trying to hook and protect. And a lot of some examples are like cookie storage, caches from request objects, document interactions API, which I'll get into further, iOS snapshots, and keyboard caching. But what about keychain data? Should I be hooking keychain data as well? Yeah, of course. So one of the main features, the main principles I mentioned earlier is that you should never rely on security features. And the only way keychain data is actually really protected is if data protection is enabled. And data protection is only enabled if the developer chooses to enable it, and also if the device has a passphrase set on it. Another thing to keep a lookout for are file names. They should probably be encrypted too. So let's look into document interaction APIs. High-level overview of this is you might encounter any iOS app can register to handle a file type. So let's say you're good for enterprise. They say, I want to handle all PDF files. So whenever you open up a PDF file in iOS, you get this nice little drop-down that says Open In, and you get to pick all the from all the apps that say they can handle it. So GFE actually implemented a handler for files that allows it to write to the GFE secure container to just store an encrypted version of it, or actually just have it emailed out to corporate email through the GFE. So how does document interactions actually work? Behind the scenes, how is one application getting this file from another app? Doesn't that violate the iOS sandbox? One app is never supposed to have access to another app. So behind the scenes, what the iOS operating system does, it actually makes a copy of that file into the GFE sandbox, and it writes it to the document/index folder. And this all happens very seamlessly. From the coding level, they have no idea this actually occurred. They just know, all right, cool, I have a file. Let me do what I need to do with it. So it turns out that this file just persists and good for extended period of time, and it's never actually stored encrypted. So even though GFE has an encrypted version of that file, the decrypted version is like the next directory down. Here's another example from a custom solution we encountered. They had a secure container, it was pretty well developed. The key thing was they forgot about the NS HTTP cookie storage object. So why is this important? If a server ever sets a persistent cookie, that cookie gets stored in plain text on a device in the cookies.binary cookies file. And obviously, cookies are somewhat important in the web because they handle authentication. So you're storing like the keys to the kingdom unencrypted on your supposed secure container. And obviously, since they never took that API into consideration, whenever a data wipe was triggered on the device, it never removed that data as well. Let's get into the home stretch for the presentation. So what are some limitations for containers? iOS has had some issues where you could only run code while it's active. So if I have an application in the background, how is it supposed to determine I should do a remote reset wipe or something like that? There's really no way for it to determine that. But iOS 7 actually provided some new background features to help with that. They added in some new background mode capabilities. One was background fetch. Now, applications that are running in the background can do periodic fetches to the server, and then get responses back and run code against it. So this seems like an actual nice scenario to actually implement remote wipes, since you can have an app, you lose a device, as long as it's still connected to the network, it could pull and determine whether it should be wiped or not. And even another approach that was added was remote notifications got built on top of. Now you can the way it used to work before is you get a remote notification, the app can't run any code until a user clicks that notification and runs the app. Now you can actually have push notifications to actually execute data upon receiving it, which sounds awesome on paper. The problem is it's not really or scalable for like application wrapping, because in order to set up remote notifications, you need a push notification server, and every single application needs a certificate, push notification certificate, in order to actually have this pipe through Apple and sent to the device. So it's not very scalable. And you leave here with one key thing is all client-side policies can be bypassed. All client-side security can be bypassed. If you're trying to enforce policies on a device, there's a million ways to actually bypass it. Pick your poison. As the policies are being sent from a server, I can modify it over the wire before it reaches the device. The device will probably need to store that somewhere. I can change it on the file system, or I can just hook into the application and just modify the function as I please. So keep server-side checks, keep policy enforcement server-side if possible. Can't always do that, of course. But if you have some critical piece of code that you want to try to protect, try to keep it as low level as possible. Objective-C, as I showed you before, is super easy to reverse. Just by dumping out the class files and hooking, you can do a lot of damage. How about jailbreak detection? Most of the stuff I showed you today requires a jailbreak on a device. So if you can provide good jailbreak detection for a secure container, you're at a better place you were than if you didn't, because now it makes it that much harder for a user to actually get any data out of there. So Cydia has like this application called XCon, which is just used to bypass jailbreak detection. So if you're like running like HBO Go or something like that, and it's like, oh, I can't run this because I'm jailbroken, people commonly download XCon and it bypasses it for you. So a good test, a simple 1, 2, 3 test is this secure container able to bypass XCon's jailbreak detection? If not, then it's pretty bad. And then, ideally, you want this detection to be as low level as possible. The lowest level you could possibly go is assembly. And there's this awesome tool out there from the guy who created this tool called Snoopit, which is pretty awesome. But it's a tool, it's like an online GUI. You just go there, and it's point and click, and it actually generates jailbreak detection in ASM that you can just copy paste into any function you want in your code. It also provides anti-debugging, so it can detect whether a GDB has been attached to a process or not, which is pretty cool as well. Thanks for coming. Come visit the GDS Consent Safely booth if you have questions, want to chat, want bottle openers. We're next to the bar as well, so that's always nice. GDS blog, I'm going to put the slides on GitHub and probably do a follow-up blog post just giving a high-level overview of the talk again. Yeah, I'm also on Twitter. I don't tweet much, but yeah. That's it. Thank you. I'm not going to lie to you. I haven't really looked into that too much. I think one of the main things was data protection is on by default, but it's not the most secure way it could be enabled. The way it was before, it was anytime you write a file to and you would have to, a developer would actually opt in to use data protection. In iOS 7, it's now on by default, but it sets it at a pretty not the best level of protection you could possibly do, but it's better than nothing. Um, there's a lot of new functionality that we haven't really looked at. There's like AirDrop has been added, so apps can now like send files to other apps. Um, but other than that, is there anything in particular you're looking for? Keychain management. So you're talking about like the online keychain? That well, the main risk that we're trying to avoid is that you can't really protect the keychain data unless you have a passcode device. Sure, it's going to be encrypted, but if the encryption key is not derived off a passphrase, it's once again it's just stuff on the device that I need to put pieces together, derives that key, and get access to the data. Once I have a passphrase, I now have additional security. Now a user has to actually guess and brute force my passphrase in order to get the access to that data. So that's the key difference. Uh, so no. Yeah, that was an interest. So they were aware of it. In terms of fixing it, I'm not sure yet. I don't have a personal copy of Good, unfortunately. And this was found during an assessment of someone's Good deployment. We reported it to them. We kind of lost communication over after a while, so can't confirm whether it's fixed yet. Well, the I would say good is pretty good. um, I don't want to talk about the other ones that well. Mhm. Thing is, you can if you implement it the proper way, it doesn't matter if your device is jailbroken because if you're developing your secure container that's protecting the data based on a passphrase, you're now forcing them to have to know that passphrase in order to get access to that data. It's for cases where it's a bad implementation and they're just relying on the fact that they need to reverse engineer the app to figure out how to actually get my data. They're relying on that as their main security mechanism. Then that's when jailbreaking is like, I can do this easily, here's how. But if you implement it in the proper way, being jailbroken shouldn't really matter. It should just be like a defense in depth approach. You're right. Oh, yeah, you're right. It's at that point if you have some form of malware running on a device that could listen to stuff that's occurring on a device, like entering a passphrase, for example, you're I don't think there's really anything you can protect. That's why I kind of recommend you have some form of jailbreak detection, and the better it is, the better off you are. Um, if you don't have that and you want to allow jailbroken device, you have to accept that risk that this code is going to run on the device. If there is some form of malware out there for iOS, which at the moment I don't think it's very prevalent, you either accept the risk or you don't. If you find out in the news that there's crazy malware going around for iOS, you might want to reconsider your approach at that point in time. And this is at an app level or at the app level? It's essentially the same. I just, if I would have done Android, it would have been a 2-hour presentation. But so I just stuck with one, and I like iOS best, so I stick with that. But it's the same stuff applies in terms of like secure containers. So you can pretty much do the same things. But from a developer standpoint, it doesn't have as many like data protection APIs, like ways to code securely as iOS has out of the box. But it's obviously it's a little more susceptible to malware based on the research out there. So keep that in mind. Yeah. If they use like if you're writing to the keychain, you can set data protection attribute. If you're writing to the file system, you can set the data protection attribute. Um, they're opting in to use that as that level of protection. It's going to be encrypted. All data on the device is essentially encrypted, but it's encrypted using a device key. The moment you turn on the device, it has that key in memory. It's able to decrypt everything. What data protection does is it's now encrypting data using another key that's derived from the passphrase. So you can only access that data once you unlock your phone at the most secure mode. Every time you lock your device, it wipes that key from memory. You now have to unlock it again to get access to that data. So it might provide some like development issues if you require, especially in iOS 7, if you require some background processing on data and the device is locked, it's probably not going to work as expected. Yeah, you have 4 different levels. Yeah, that's if you have a developer and you're trying to develop your own apps, data protection is the way to go if you don't want to roll your own crypto, because stuff can go very wrong when you do that. The key thing is you have to keep in mind your customers. Data protection is only going to provide good security if they set that passcode. Some of them might set it, some of them might not set it. Yes, but then if you use data protection, it's relying on the device passcode, not the application passcode. If you're using an application level passcode, you have to do your own crypto at that point in time. Yeah, once you have enterprise like MDM and stuff like that, you can enforce policies on devices. Then you're at a better. You can say all these devices have to have a passcode protection. You have to have this password complexity, and then it kind of solves the solution, the issue of secure containers. You no longer really need this. You're enforcing policies on these devices at that point in time.